Okay, hello everyone. So before we leave the topic of the spectral theorem entirely behind, I wanted to just do one video on a very important application of spectral theory to analytic geometry in higher dimensions. So by analytic geometry, what I mean is the kind of thing you studied in Algebra 2 for the plane. It's where you use coordinates, use the standard rectangular coordinate system or Cartesian coordinate system in the plane that's just x and y, right, the x and y axes, to study the geometry of various shapes. So, for example, you can write the equation of a line in various forms, but they're always first-degree equations in rectangular coordinates, right? And you can write the equations, like certain quadratic equations, in two variables, which turn out to be the conic sections, and they have interesting geometric properties. Okay, so, of course, we can only just barely scratch the surface of analytic geometry in 3 dimensions and higher. After all, you spend virtually a whole semester or more doing very simple analytic geometry in the plane. And you sort of, in pre-calculus, barely scratch the surface of various higher curves that exist in the plane, such as lemniscates and other things that require polar coordinates for their description. So there's a very rich subject there. Analytic geometry, even in the plane, is extremely rich and has a tremendously interesting history. Okay, we obviously can't approach anything like that, but I wanted to just give you a taste of one particular topic, which is a very nice generalization of something you learned about in detail in pre-calculus. Namely, you learned in pre-calculus the conic sections, how we classify them into 3 main groups, the ellipses, the hyperbolas, and the parabolas, with various sort of degenerate cases that are possible. So by degenerate cases, I mean things like a pair of crossed lines can count as a conic section. And you can see it when you look at that famous picture of a plane slicing through a cone. If you happen to slice right through the vertex, perfectly vertically, something like that, then the curve of intersection will be exactly, something like that, right? The union of 2 crossed lines. So there are various things. Another degenerate conic section is if you slice the plane through the cone this way, you'll get like a 1-point curve of intersection, a singleton set. That has to be counted as a kind of degenerate conic section as well. And there are a number of these. But you have 3 main families: ellipses, hyperbolas, and parabolas. And then again, a number of smaller degenerate cases. So the question is, can this be done for quadratic equations in 3 variables? Let's say these conic sections are the graphs of quadratic equations in 2 variables, x and y, because we only have 2 axes. So if I write down some quadratic equation like this one, let's say it's linear in y and quadratic in x. Maybe it has a constant term, right? So that's a parabola. But essentially any equation of degree 2, which can have degree 2 terms, including an x times y term, right? It can have an x squared term, a y squared term, you can have x, y, and then constant. So any combination of those, basically set equal to 0. We can classify that after an appropriate rotation and translation to get the thing into standard position. Then it can be classified as either an ellipse, parabola, or hyperbola, or some degenerate case. And I think you saw some small taste of that in pre-calculus when you talked about rotation of the axes. And there, I think you determined explicitly a formula for the angle of rotation that will bring the conic section into so-called standard position with its axes of symmetry parallel to the x and y axes. So we want to do something like that in 3 dimensions, and also in higher dimensions, although a complete classification is very difficult in higher dimensions. But we can do a complete classification in 3 dimensions, and we will in this video. Right? And we can also gain some insights into how it works in d dimensions generally, although obviously visualizing is difficult. Well, actually visualizing is impossible in 4 dimensions and higher. Nevertheless, we can write down all the important qualities that go into a classification scheme. And with enough work, we can actually write down the classification explicitly. So we'll do that in 3 dimensions because it's a manageable problem. And actually, maybe we should also do it in 2 dimensions when it's a very easy problem, just to get some practice with it. And then I'll just leave it to you, if you want, to try to work out the classification scheme in 4 dimensions. I think that's a very worthy but difficult exercise. But this will give you at least the flavor of what we might call quadratic geometry in higher dimensions. Right, so it's part of this topic of analytic geometry, but in particular it's just quadratic geometry. And what I mean by that is that it's studying equations of degree 2, algebraic equations, specifically of degree 2. Now, there is, of course, an analytic geometry of cubic equations, but that's much, much, much harder, and much less is known about that. There are all kinds of interesting theorems that are known about equations that have, let's say, x to the power 2 and y to the power 3. And so those are called elliptic curves. Some of them are. And they're of great importance in number theory and other branches of mathematics. In fact, they played a role in the proof of Fermat's last theorem. But that theory is very, very difficult and certainly well beyond anything that we can do with the tools we have. So let's stick with quadratic geometry. Of course, there's also linear geometry, right? Degree 1 geometry, and that's basically just linear algebra from a geometric standpoint. So linear algebra can be viewed, of course, as algebra. Matrices have an algebra to them. We can add them and multiply them and so on. But we can also view linear algebra from a geometric standpoint, because after all, a matrix just is a representation of a transformation from one Euclidean space to another. And oftentimes these transformations have simply visualizable properties. So the geometry of those properties, of those mappings, can be viewed as a kind of linear geometry, first degree. Okay, anyway, so we're going to talk, just scratch the surface of quadratic geometry now. And so let's begin just in the abstract setting. We're going to work in d dimensions, and then we'll specialize to 2 or 3 dimensions to get specific classification schemes. But, in d space in general, a quadratic equation is an equation of the following form. So we're going to have some coefficients, a sub I, and then all the variables xi squared, I running from 1 to d. So those are the pure square terms. All right, then we're going to have cross terms, which will look like this. You'll have some coefficient bij times xi times xj, where I and j differ, and I'm going to choose I to represent the smaller of the two. And of course, they both have to be between 1 and d. And the coefficient of 2 here is just convention. We don't have to write it, but it's conventional to write that. And the reason is because since I forced I to be less than j, there's these two terms, and then there's also bji, xj, xi. And by replacing the bij's with, let's call it bij tilde, which is the average of bij and bji, then we can put the 2 on this side and basically combine those terms, because these products are the same. So basically those are like terms, and you can combine them. So then you can just rewrite that term with this coefficient. But it's just that the tilde is being erased to hide the evidence of this process. So that's where that 2 comes from. Okay, so those are what are called the cross terms. And they're called that because they cross or mix 2 different variables, xi and xj. All right, then we're going to have linear terms. So some linear combination of all the variables. Well, okay, let me write it with I. Ci times xi, where I runs from 1 to d. So those are first degree terms. And then finally, there's a constant term, which I'll just call d. Well, I can't really call it d because I called the dimension d. I'll just call it p. All right, and then you just set the whole thing equal to 0. So this p is the constant term. All right, so such a thing is a quadratic equation. And to make it truly quadratic, we want to make sure that it's genuinely of degree 2, meaning that not all of the ai's and all of the bi's are 0. See, if all of the ai's are 0, and also I said bi's, I meant bij's. If all of the bij's are 0 in addition, then there are actually no second degree terms at all. The whole equation would just reduce to first degree terms and 0 degree terms. And then we wouldn't want to call that quadratic equation. So we have to impose some condition to make sure that those things don't happen. Okay, so we'll say where either some a sub I is different from 0, or some bij is different from 0, or both. So there's at least one quadratic term present. But there don't have to be any linear terms present. In other words, it's okay for all the ci's to vanish, and it's also okay for p to vanish. That still fits into the terminology of a quadratic equation. All right, so the question is, what does the graph of that look like? And by the graph, I just mean like the set of all solution points. So by the graph, I mean, let me just call it S. It's like the set of all points x in D space that satisfy that quadratic equation. So let me just call the function on the left-hand side f for short, and the whole thing is being set equal to 0. So by f of vector x, I just mean this expression. Okay, and x is the vector x1 through xd. Okay, so anyway, the solution set of the equation is its graph. And this is, by definition, a quadratic hypersurface, is what it's called. This S is called quadratic hypersurface. Sometimes also called quadric. It just differs from book to book, author to author. Okay, now you should just ignore the term hypersurface for now. What the meaning of that term is just like some curved set of dimension exactly 1 less than the dimension of the space it sits in. So for example, a curve in the plane is a hypersurface. A surface in 3 space is a hypersurface. Actually just called a surface without the word hyper. Because you see, a curve is of dimension 1. It's a kind of one-dimensional set, although it's curved. It's not a straight line, which is the kind of paradigm case of a one-dimensional set. But it's kind of the image of a straight line under a smooth map. You can think of there being a parameterization, where this curve is parameterized by, let's say, with respect to time. And then time is describing a line, which is one-dimensional. And then the image of that set is also one-dimensional for that reason. But notice that it's a one-dimensional object in two space, so the dimensions differ by precisely one. And then again, a surface is a two-dimensional object, and it's sitting in three ambient dimensions, so that fits the bill as well. A three-dimensional curved object is sitting in four space, would be called a hypersurface. And in general, a d-1 dimensional manifold, as we call it, sitting in d space, is called a hypersurface. So it turns out that this is that, like this type of set really is a manifold of dimension d-1. But I haven't defined manifolds in general yet, so we don't have the tools to understand this very precisely at the moment. But I'll just make a remark, not a formal claim that has to be proven, but just a remark for the future, that this will turn out to be, and we will prove it later, a manifold, which is sort of one of these curved objects, like a curve or a surface, but it's of dimension d-1 in d space. And that's what a hypersurface is in general. Right, now, we can't really prove that formally. We don't even know what a manifold is yet. But yeah, it will be proven as soon as I do define a manifold, which is coming up kind of next. That's the next big topic. All right, so just ignore the hypersurface part. Just think of it as the graph of a quadratic equation. And the task is to classify and try to understand, what S looks like geometrically, graphically. Okay? So it's a little bit of a vague task, but you'll see when we work out the classification scheme in 2 dimensions and 3 dimensions, you'll see exactly what I mean. All right, so the first thing we should do is put this equation f of x equals 0 into more manageable form using linear algebra. And so this term is quite easy to do that to, because you'll recognize that simply as a dot product. If you take all the coefficients c sub I and make a vector out of them, so this vector c has c1, c2, up to c sub d as its components. And we can also write that as a matrix product by writing it in the form c transpose times x. So that term is very, nice from a linear algebra standpoint. Right? Also, I claim that these terms are also nice because they simply are a quadratic form. Notice that you have pure square terms and then you have cross terms. So you basically have all possible terms of degree 2 added together with certain coefficients. And that's precisely what a quadratic form is. Now, we already know how to write a quadratic form in a compact way. It's just x transpose times a times x, where a is a certain matrix, a d by d matrix. And let me just write down what that matrix looks like a bit more explicitly here. The matrix A is going to have a1, a2, and so on, up to a sub d on its main diagonal. And then we'll have like b12 and b21 up to like b1d and down to bd1. Well, let me write something like this is b2d, and this would be bd2. Right, but b12 is the same as b21. This is a symmetric matrix because we chose it that way. If you recall the argument, when we wrote the cross terms in this form, when we wrote the cross terms in this particular form, I showed you this argument that said that, if you just have two unrelated terms involving I and j, so the argument was that these two products are equal, so these are like terms, and you can just combine those terms. And the total coefficient would be the sum, bij plus bji. And then by writing that as 2 times the average, writing the sum of those two numbers as 2 times their average, you get this coefficient of 2 here. And then this bij that's written in here is really just the average of these two, just renamed as bij. It's a little confusing, the notation, but basically what you do is you take the average of these two original given ones, and you replace both of them by their average. And that allows you to write the cross terms in that particular form. Okay, but it also means that both the original b12, let's say, and the original b21 have both been replaced by the average of the two. So the new b12 is the same as the new b21. In other words, after this replacement, the matrix A can be written as a symmetric matrix. Right? And more generally, bij is now equal to bji because they're both the average of the two original quantities that were given. I hope that makes sense. The notation is a little weird because I'm using the same symbol bij for like both what was given to me originally and what remains after I do this. little move of replacing those by their average. But okay, I hope that makes sense. I think we did it in class anyway. So the point is that we can take the matrix always to be symmetric. So we'll just write that this A is a matrix of size d by d, and it's also a symmetric matrix. And that's why we can apply spectral theory to this classification problem, specifically because we have a real symmetric matrix, and we have spectral theory about that exact situation. Okay, so now our function f of x is expressed this way. There's this quadratic form, which let's also denote for short as q sub a of x. That's the quadratic form based on the symmetric matrix A, right? And then you have this product, C transpose times X, giving the linear terms, and then there's a constant P. And then we set equal to 0. So that puts the equation into a nice compact form. All right. Now, the first thing we're going to do is use the principal axes theorem. And remember, what that tells us is that there exists a rotation, R. Well, okay, I should be very careful. The rotation is the linear map based on the matrix R. A rotation, after all, is a mapping. It's a transformation from D space to itself. So the word rotation really should be reserved for the actual mapping from D space to itself, based on that matrix. But it's based on a so-called special orthogonal matrix, capital R. So it's SO of D. So remember what that means is that it's an orthogonal matrix. So this consists of all matrices d by d that have the following properties. X transpose equals X inverse. That's the orthogonality property for a matrix. And then also the determinant is 1, positive 1, as opposed to negative 1. Okay, so that's the special orthogonal group. And we also call those rotations. Rotations about the origin. Well, then, okay, those are rotation matrices. And then the linear map based on a rotation matrix is a rotation as a mapping from D space to itself. And we know about those mappings. We studied this earlier. We know that those mappings fix the origin, preserve all distances, also preserve all norms, and also preserve orientation. Every frame, every oriented frame or ordered frame has its orientation preserved when you map them under this rotation. Okay, so there exists a rotation, and there exists a diagonal matrix, capital D, which will have diagonal entries lambda 1 to lambda d, okay, where these are the eigenvalues of the original matrix A, which let's recall is symmetric. By assumption, okay, but they have to be listed according to multiplicity. Okay, what that means is just that if a particular eigenvalue of A has a multiplicity of 3, then you have to write it 3 times in that list. But here's the thing, is that it's in some order. See, you can order those eigenvalues with the multiplicities counted in any order you like. This is just like in some particular order. It doesn't have to be in any canonical order. In fact, the order depends on the rotation matrix. If you remember back from the proof of this principal axes theorem, basically, if you had a particular ordering of the eigenvalues listed by multiplicity, the matrix that we constructed originally, this S, either had determinant 1, in which case you could use it as R and just be done with it, or if S had a determinant of negative 1, we had to like swap its first 2 columns. So R was the result of taking S and swapping its first 2 columns. But then you also have to swap the first 2 eigenvalues in your list, lambda 1 and lambda 2. So basically, the order in which you list the eigenvalues will depend on the particular rotation matrix, capital R, that you use. The two are connected to each other. The R and the D come as a pair, and they're correlated with each other. Okay. But such that the quadratic form based on the original A, matrix A, can be expressed as the quadratic form based on this diagonal matrix D evaluated at R times X. That's the key equation. And another way to write this, the important thing about the quadratic form based on a diagonal matrix, if you look at a diagonal matrix, has entries only on the diagonal and zeros everywhere else. So if you write down the quadratic form, let's say in some new variable y, you find that you're just going to get lambda 1 times y1 squared, lambda 2 times y2 squared, and then lambda d times y sub d squared. They're only pure square terms, in other words. There are no cross terms, because the cross terms would have these coefficients, and they just vanish. So anyway, means that this is now like lambda j. J will run from 1 to d. But it's lambda j times, you have to take the vector r times x and pick out its jth component, and then square that. So this r times x is what I called y down here. And then you have to pick out like the jth component of y, which is yj, and square that, and then you'll have lambda j. So anyway, that's the that's a good way to understand the result, is that you can, by doing this rotation, replacing x with r times x, you get the quadratic form to be written with pure square terms only. No cross terms. And that makes it much, much more pleasant to work with. Remember, the original quadratic form had cross terms, perhaps. I mean, it didn't have to, but it could have. But now this new quadratic form has no more cross terms, and that's good. Right, so anyway, that's the principal axes theorem, and now we're going to apply that. And we're going to say the following thing. So actually, as a first step toward a classification, we can say the following thing. We can say that if some particular a sub I is equal to 0, right? So in other words, there's no pure square term there. Oh, I'm sorry. Let me slow down a bit. What does our set S now look like? Okay, so remember, it's the set of all x that satisfies the original equation, which was this. Okay, now what I want to do is write this set in terms of the variable y, where y is r times x. Okay, so the rotated version of x, in other words. It's like a rotation of the coordinate system. X is representing an arbitrary vector in the given coordinate system, and then you're taking that vector and rotating it. Now, you can view that, there's sort of two viewpoints on this. There's the active transformation viewpoint, and then there's the passive transformation viewpoint. The difference is that with an active transformation, you're taking the vector itself and moving it. With a passive transformation, you're taking the coordinate axes and rotating those while leaving the vector fixed. But you see that those are the same thing, as long as you do the inverse rotations. Right? So like in the plane, for instance, if I have a particular vector, I can either actively rotate that vector here, or I can, so in other words, that rotation will go this way. Okay, or I can take the axes and rotate them the other way by the same amount, getting a new pair of axes. Right? And then the black vector hasn't moved anywhere, but the black vector with respect to the yellow axes is the same as the red vector with respect to the original axes. So basically the active viewpoint and the passive viewpoint are just equivalent ways of viewing things, but we're going to always look at things from the active viewpoint. However, behind the scenes, you should really think of it as a passive transformation. It's like a rotation of the coordinate system, but we're just not doing it that way. We're doing it the other way because it's easier. Easier to pick up one vector and move it than to pick up the whole coordinate system and move it. But again, the two points of view are really equivalent. All right, so I'm doing this from the active viewpoint. I'm actively picking up the x and rotating it by r. So anyway, let's remember that if I multiply both sides by r inverse, oops. So of course, these two cancel. They give the identity matrix. But let's also remember that R inverse is the same as R transpose, because it's a rotation matrix, is in particular an orthogonal matrix. And it's easier to think of it as R transpose. And then on this side, it's I times X, or it's simply X. It's easier to think of it as R transpose because it's very easy to compute the transpose. If you know the original matrix, the transpose takes basically no work to write down. So whenever we can get away with that, we should. Anyway, so we can replace all occurrences of X by this. Okay, so our set S becomes the following thing. It's like R transpose times Y, such that this equation is true. Okay, and then also let's realize that this term here can be simplified because Q sub A of anything is the same as Q sub D of R times that thing. And it just so happens to be this thing that we're plugging in. But I'm using this identity here in this box. I just happen to be replacing X with R transpose times Y in both places. Okay, and so, the R and the R transpose just cancel out. They're inverses of each other. So that term just becomes Q sub D of Y, which has, again, pure square terms only. And we can also simplify the linear term a little bit. We can write it as like R times C transpose times Y. And, okay, that's simply because, the product of these two transposes is the transpose of the product. But you have to reverse the order of the product. That's one of the basic rules of transposes. Right, and let's also rename this. This is some vector. I'm going to rename that as K. So let's define K as R times C. It's a vector because this is a D by D matrix and this is a D by 1 vector, so the answer is a D by 1. In other words, just some vector in D space. Let's just call it K for simplicity. All right? So now our set S looks like this. First of all, also I can sort of take the R transpose to the outside. Now I'll explain what I mean by this in a minute. But we then have this quadratic form based on the matrix capital D, and then I have this vector K transposed times Y, and then I have P. Okay, all in sort of big square brackets. Yeah, maybe I should write it as a linear map based on R transpose. Okay, so what I mean by these big square brackets here and here is the image of a map. Sorry, the image of a certain set under a map. basically I have this set here inside, which let me call capital T. And then I'm plugging that set into the map, this map here, which is a rotation of D space. You see, it's a rotation because it's the linear map based on a matrix R transpose, where that matrix is an orthogonal matrix, and in fact a special orthogonal matrix. Right? You see, because R was a special orthogonal matrix, and R transpose is just the inverse by orthogonality. Now, the inverse is also in the same group. See, the SOD is a group. We talked about this in a prior video. But basically, it's closed under multiplication, and the identity matrix is in it. Okay. Why is it closed under multiplication? Well, if X transpose is equal to X inverse, and X has determinant 1, and let's say I have a second matrix Y with the same exact properties, Y transpose equals Y inverse, and determinant Y equals 1, you can easily prove that X times Y has the same exact properties. You see, X times Y transpose is Y transpose X transpose, which is Y inverse X inverse, which is X times Y inverse. So the product X times Y has the property that its transpose equals its inverse. And it also has the property that its determinant is 1, because remember that the determinant of a product is the product of the two determinants. That's the multiplicative property. But since those factors are both equal to 1, the product is 1 as well. Okay, so anyway, you see that because it's a group, okay, well, I guess I sort of explicitly need to check as well that it's closed under inversion, which is kind of the claim here anyway. If R is in that group, then so is R inverse. Why is that true? Okay, it's easy. It's just because, R inverse also has the property that its inverse equals its transpose. Why? Because its inverse is R. And that is R transpose transpose. But then R transpose is the same as R inverse. So you see that R inverse has the property that its own inverse equals its own transpose. And it clearly has determinant 1 as well, because the determinant of the inverse matrix is always 1 over the determinant of the original, and if the determinant of the original is 1, then the reciprocal is 1 as well. Okay, so it is a correct claim. Anyway, so we do have a rotation. It's not the original rotation, it's the inverse rotation. This is not the original rotation. The original rotation was the one based on R. This is the inverse rotation of that. But we have this set, capital T here, and then we have the image of that set under a particular rotation of D space, and that gives us back our given, quadratic set, our given quadratic hypersurface. And let's also notice that T is also a quadratic hypersurface. It's just much simpler because the quadratic form involved. Okay, so in other words, it has the same form. If I take this entire function of y and just call it, say, g of y, it's not vector valued, it's just scalar valued. Okay, so that g of y has the same exact form as f of x did. The first term is a quadratic form in y, based on some symmetric matrix, just so happens to be the matrix D. The second term is some row matrix of constants times the vector y, and then the constant term is there. So you see it's also a quadratic hypersurface, the set T. It's the set of all solutions, or the graph of some quadratic equation. It's just a quadratic equation in y instead of in x. And it's significantly simpler than the original quadratic equation because this matrix D is diagonal. Okay? And then all you have to do to that set T, all you have to do to that particular quadratic hypersurface is rotate it appropriately by this particular rotation, which is known. And that will give you back the original quadratic hypersurface S that we started with. So you see that by a rotation of the axes, we can put the given quadratic hypersurface into a kind of standard position, or standard form. And that standard form involves only a diagonal quadratic form. No cross terms. So our quadratic equation now will look something like this. It has lambda 1 y1 squared up to lambda d yd squared. Then it will have k1 y1 up to k sub d y sub d, and then plus p equals 0. And we're just considering the set of all y in space that satisfy that. That's the T. Okay, so let's call this T the standard form of the original set S. I'll just use that terminology. If we understand the geometry of T, we understand how that looks, then we also understand how S looks, because S is just a rotated image of T. All right, great. So from now on, we're just going to devote ourselves to understanding this equation here, the solution set of that equation. Right? No cross terms. Now there's one more step we can do to make the equation simpler, which is the following thing. You see, y1 appears twice in this equation, once quadratically and once linearly. And if lambda 1 happens to be non-zero, so that that quadratic term is genuinely there, genuinely present, then we can complete the square in y1. Right? We can basically take lambda 1 y1 squared and plus k1 y1. We'll factor out lambda 1, writing this, and that's acceptable because we know that lambda 1 is not 0, so it's okay to divide by it. Okay, and then, whoops. Inside here, we take like half of that coefficient and square it. So what do we get? K1 squared over 4 lambda 1 squared. But then you have to subtract that very thing, except that now you don't write a square here. You leave that unsquared because this lambda 1 has to distribute anyway. So that will compensate. And I haven't changed anything. Right? But notice now that this factors as y1 plus a certain constant squared, and then I have minus a certain constant. And then what will happen is that this constant here, including the minus sign, will just absorb into the p, into the constant term p of the original equation. So the constant term will change, of course. But the advantage is that if I rename this variable here as, let's say, y1 tilde, just call that new variable that, right? Then that term accounts for both of the y1 terms in the original equation in a single term. And that term looks like this: lambda 1 times y1 tilde squared, right? With an appropriate change to the p, to the constant. All right. Now, we can do that for every pair of variables as long as the quadratic term, not every pair, every variable. y1, we do it, then we do it for y2, then we do it for y3, as long as the quadratic term is genuinely there. If one of these coefficients, let's say lambda 2 happens to be 0, then the y2 squared term is not genuinely present, because that is a 0. And then you can't do it. Then like the k2 y2 term over here has to stay. You can't absorb it into the quadratic term. So essentially you're going to get rid of all the linear terms, except for those linear terms involving a variable that doesn't have a quadratic term. Right? So for instance, if there's no quadratic term y2 squared, then you'll have a linear term in y2, namely k2 y2. But if there is some y2 squared term, then there is no need for a linear term because you can absorb it into the quadratic term by completing the square. Right? So we can go through all the variables and just do that, complete the squares whenever possible. All right, and then we'll have a new set of variables. Okay, now any variable that we didn't touch, like for example, let's say y2 remained untransformed, then we're just going to introduce a notation y2 tilde to stand for y2, just as alternative notation. And the reason for this is just so that I can have a consistent set of, like, I have this first original set of variables. Actually, my first set of variables really was the x's. But then I've replaced the original set s with this other set t, which is the standard form of s. So now I have this other set of variables. And now I'm going to yet another set of variables. And I want to have a consistent notation for those. I want to call them all tildes, y1 tilde, y2 tilde. So basically, yj tilde is going to be either just yj again, if lambda j happens to be 0, so that there's no square term in yj. Or it's going to be yj plus a constant, which happens to be kj over 2 lambda j, if lambda j is not 0. Right? And so notice that the vector y tilde, that's an awkward notation, because I have an arrowhead symbolizing that it's a vector, and then a tilde over that. It's a little bit of an awkward notation, but it's okay. Anyway, the vector y tilde, which just has these components, is simply a translated image of the original vector y, which has these components here. So it's like y plus something. And what should I call this something? Oh, I don't know. Let me say t for translation vector. Right, so it's just a translated image. And what does our equation look like now after we perform this transformation? Right? So you see that we have to invert this equation. We have to write y in terms of y tilde. We do that by just subtracting the vector t. So this vector t is by definition the vector with these constants in it. Okay, so it's a bit hard to write a formula for this because each coefficient or component is like a piecewise formula. It's either 0 if lambda 1, let's say, is 0, or it's k1 over 2 lambda 1 otherwise. And then you'll have all the other components like that. Right, so that's the translation vector. Anyway, by subtracting that vector over to the other side, we can solve for y in terms of y tilde. And now our quadratic equation, let's see what it looks like. The original quadratic equation would have looked like this. And if I just replace y, I'm sorry. Yeah, so this equation is equivalent to, okay, so it's the same quadratic form with y tilde plugged in, and then some modified constant, which we can call p tilde. Or well, for simplicity, maybe I'll just call it q. Okay, so those two equations are equivalent, because you see that these represent all the quadratic terms involving the y, the original y's, and these are the linear terms involving the y's. But those got combined through this completion of the squares process. But of course, the constant p in the original equation had to be modified accordingly, because that p has to absorb all of those extra constants, these, right, from each term, or each term with a non-zero lambda. For every non-zero lambda, essentially, there's a term of this type that has to be absorbed into the p. So basically, this q is the original p, and then it's going to be a certain sum of constants of the form kj squared over 2 lambda j. But it's not for all j, it's only for all j such that, okay, let me write it like this. It's like you sum over all j for which lambda j is not 0. Yeah, so that's the definition of q. But the important point is that these terms combine into these quadratic terms. The coefficients are the same, which is why it's the same matrix D, the same diagonal matrix. Because you see that the terms that result are terms like this: lambda 1 times y1 tilde squared. Okay, so in other words, this quadratic term and this linear term, the sum of those two together, get replaced by a single quadratic term, which looks like this. When we add those together, right, we get this. Plus a constant. And that constant gets absorbed into the p. All right, but notice that the coefficient of the quadratic term is still lambda 1, so that didn't change, which is why the diagonal matrix, capital D, is the same. Okay. It's just that you now have basically a pure quadratic form, plus a constant equals 0. Or maybe we can write it a little bit more compactly by moving the constant q to the other side. So we can just write it like as basically that's equal to a constant. Well, let me still call the constant q. And the difference now is that I'm taking all this and negating it. So let me redefine q as the negative of what it was before, so that I can basically write it on the other side of the equal sign. Okay, so it's the same thing. Good. So now that I've got the equation in this form, and I know the relationship between y and y tilde, we can consider a new set. Remember, we have our set T. Well, originally we had the set S, and then we had this new set T, where g of y is that function. Okay, and what we can then do is we can just write this as y tilde minus t, and then just put here the equation involving y tilde. That's equivalent to the equation g of y equals 0. Right, and that equation is q sub d of y tilde equals q, where q is just some constant. Right, and now the key thing is to think of this as a translated image of a set in which it's the y tilde that's constrained, rather than y tilde minus t that's constrained by some condition. You see, all I've done really here is, everywhere there was a y, I just replaced it by something equal to it. This is simply y again. So I'm just still considering the set of all values of y that satisfy some condition. This is still the value of y, just being rewritten differently. And this is the same condition, essentially. It's just because these two equations are equivalent to each other. So I haven't really changed the condition. I haven't changed anything at all, which is why I have this equal sign here. I've only changed the way that things are written, the notations. But now you see that we can regard this as the set of all y tilde that satisfy that given condition, but with something done to it, and namely translation by the vector negative t. And then you take the image of that whole set. Right, so I have this new set here. This set inside is not the same anymore. I'm going to call it capital U for short. So I'm essentially writing the set capital T as the image of capital U under some map, and this map is the translation by the vector negative t. Right, so notice that it's not the same translation as the plus t before. It's the inverse translation of that. It's translating by the vector minus t. But nevertheless, it's just some translation that we know. We can calculate the vector t. We have a formula for it here. It's a bit of a complicated formula because each component has a piecewise formula to it. But nevertheless, we can calculate that vector. And so this is like a known translation. And translations are isometries, so they don't change the geometry of the set. Essentially, the set U is pretty much identical with the set T from a geometric standpoint. It's just that one is a translated image of the other. T is a translated image of U under this translation. So if we understand the geometry of U, then we also understand the geometry of T, right? And remember that remember that the original S itself was the image of the set T under a rotation. So we have this linear map based on this rotation matrix R transpose. And now what we're doing is we're saying you have this rotation, and then if you compose that with a translation, then you can write the set S as a certain image of this set U, right, under some rigid map, under some rigid motion. This map here is a rigid motion, or isometry. Yes. So in other words, distances are preserved. Okay, why is that? Well, a translation is an isometry. It preserves distances. And then a rotation about the origin is also an isometry. Okay? So the composition of two isometries is also an isometry. Because if the first map you do preserves all distances, and then the second map you do successively after that preserves all distances, then the effect of the entire composition will be to still preserve all distances. So notice that not only is this an isometry, but it's a known isometry. We can calculate it, because we can calculate the matrix R transpose, so we know its linear map, and then we can also calculate the vector T, or minus T. And so, yeah, both the translation vector and the rotation matrix are things that are known to us. They're both computable. Okay, so basically, our original set S, which is the set we started with, we really wanted to try to understand the geometry of, we've now reduced that understanding to just understanding the set U. Okay, and the set U is of a very simple type. If I just restore the variable x instead of writing y tilde as the variable, because after all, what you call the variable doesn't much matter. So now that I understand that the set U is the important set, the set U is a kind of reduced case, such that if I can understand it, then I can understand all quadratic sets, all quadratic hypersurfaces, because the rest of it is simply some process that I understand, a translation followed by a rotation. Okay. Notice, by the way, that that's the active point of view. But equivalent to that is the passive point of view, where I can just think that I'm not changing the set S at all. I'm just moving the axes around, the whole coordinate system. I can translate the entire coordinate system parallel to itself, moving the axes and the origin, and then rotate the axes. So I haven't really moved the set S at all. I've just moved the coordinate system to get a different or better description of S. That's the passive point of view. We're doing something equivalent to that, but we're doing it. The thing we're doing is simpler to write down, which is the active viewpoint, where we leave the coordinate system alone, but we actually change the set S by moving it in predictable ways. You translate it somewhere else, and then you rotate, all space about the origin so that the set moves. But anyway, the point is that we get the set U here, which has a particularly simple equation. And we can write that equation in any set of variables we like. It's the same equation. It's just like we're writing it in terms of different variables. I'm going to go back to the variables x, like in other words, x1, x2, x3, up to xd, because we can dispense with this whole process now. As long as we understand the set U in itself, then we have some known procedure for going back to the original set S, geometrically speaking, namely a certain translation that we know, followed by a certain rotation that we know. Okay, so the equation, what does it look like? Q sub d of x equals a constant. Or in other words, lambda 1 x1 squared. Oh, I'm sorry. There's a little mistake here. Okay, yeah, sorry. There's actually a big mistake here. I'm a bit tired. So let me go back and correct something even from before. When I said that these two equations here are equivalent, okay, that's obviously not correct, because I'm not accounting for those linear terms in here that had no matching quadratic term in here to combine with. Remember how that worked? It was only when lambda j was not 0 that we were able to actually combine a quadratic term and a linear term through completion of the square. But in the case when lambda j is 0, that the linear term will be there, perhaps. I mean, its coefficient could happen to be 0 by chance, and so it may actually not be there for that reason. But potentially you could have a linear term there. So in this bottom equation, I need to have some linear terms. So I need to modify that equation so that it has linear terms. And it's going to, of course, have a modified coefficient vector, because all of those y tildes that were subjected to completion of the square will not have linear terms anymore. Those linear terms have been absorbed into the quadratic term. So we're going to have some new coefficient vector here, or coefficient row matrix, rather, which let me call m tilde. Okay, the q is still correct. It's given by this formula here. It's just basically you move the p here to the other side, and then you have to absorb all those constants that came from completing the square. So this formula here is still correct. But this vector m has a lot of zeros in it. Let me write it down. Where should I write this down there? I'll write it here. The vector m is going to have in it, well, it also has a piecewise formula. So, for example, its first component is going to be just the same as the first component of k if lambda 1 happens to be 0, and then it's going to be 0 otherwise. Right? The second component will be similar. It will be k2 if lambda 2 is 0, but 0 otherwise, and so on. So you can fill out that entire vector. So you see it has a lot of 0 components. These zeros come from cases where we completed the square. So if lambda 1 was non-zero, then we would have completed the square, so there wouldn't be any need for a linear term in that case. The only linear terms that are left, the only like non-zero coefficients that are left, potentially non-zero, are the ones where we did not complete the square. So like if lambda 1 were 0, then we would still have that k1, y1 term left over. Okay. Well, it would actually be k1, y1 tilde, because in that case, remember that the convention was that in any such case, where let's say like lambda 2 was 0, then the variable without the tilde is the same as the variable with the tilde. So it doesn't matter how I write that term. Okay, but yeah, they're still linear terms. But the point is that the terms that are, so here's the really, really good way to think of it. The terms that are in here that are non-zero, that really appear, genuinely appear, in that linear part, involve none of the same variables that appear in this part. Okay? Because the variables that appear in the quadratic part are only the ones where the lambdas are not 0, since the coefficients are still the lambdas. You see, the coefficients of those quadratic terms are just still those lambdas. So any lambda that's 0, like there won't be a corresponding term there. But there will be potentially a linear term for that. So you basically have two disjoint sets of variables. The y tildes can be subdivided into two classes. There are those that appear non-trivially in the quadratic part, and then there are those that appear non-trivially or potentially so in the linear part. I say potentially because the ones that appear in the linear part will have some coefficient, which I'm calling m sub j now. Those are the components of this vector. But even when m sub j is not 0, or let me say it differently. Like if this k1 is retained because there's no quadratic term, like the lambda 1 is 0, so there was no completion of the square, but k1 might be 0, just by chance, k1 might be. So in other words, the linear terms don't actually have to appear. They could just by chance not appear because their coefficient could happen to be 0. But the point is they could potentially appear. But yet, what I'm saying is that the variables that appear non-trivially here in the quadratic part of the expression, and then the variables that potentially appear non-trivially in the linear part, they are disjoint sets. Okay, so I basically can subdivide the y tildes into two disjoint sets of variables, some of which appear non-trivially in the quadratic part, and then the others of which appear potentially non-trivially in the linear part. Okay, so let's figure out a way to notate that effectively. So what I'll do is I'll just introduce new variables to account for this. And let me just call those variables like the u's and the v's. Okay, so we don't know exactly how many there are of the u's and how many there are of the v's, because it's going to depend on how many of the lambdas are 0, how many of the eigenvalues are 0. Remember that 0 could be a repeated eigenvalue. It could have a higher multiplicity. So let's say 0 has multiplicity 4 as an eigenvalue. Right? Then you're going to have 4 of those lambdas are going to be 0. Right? But we don't know in advance, right? We don't know enough about the specific matrix A to know in advance whether 0 is one of its eigenvalues, and if so, what is the multiplicity of it? Okay, so I'm going to introduce two vectors, u and v, such that u consists of exactly those y tildes corresponding to the non-zero lambdas. These correspond to the non-zero lambdas, lambda j's, and then these are the rest. Those correspond to the lambda j's that happen to be 0. Okay, now, so in other words, what I'm saying is that y tilde is some interlacing of u and v. Okay, you have to take the components of u, and you have to take the components of v, and you have to sort of interlace them in some order to get back the original y tilde. Okay, so you see that this notation is pretty cumbersome. It's hard for me to even write down the precise relationship between y tilde and u and v. But let me just tell you kind of an example. Like let's suppose that lambda 1 happens to be 0 and lambda 2 is not. and then lambda 3 is, and then lambda 4 is not. Just as an example. So then y1 tilde would be v1, and y2 tilde would be u1, and then y3 tilde would be v2, and y4 tilde would be u2, and so on. They would literally be interlaced in that way. And of course, that doesn't have to happen because these can appear in any combination. Maybe the first three of them are non-zero, and then you have a 0, 1. In that case, you'll have, right, so like, if these were all non-zero, except maybe the fourth one is 0, then you would have this order, u1, u2, u3, and then v1. So there's some interlacing, in other words. But it's the u's that correspond to the non-zero lambdas, and then the v's correspond to any lambdas that are equal to 0. All right? So obviously, that's a very cumbersome thing to write down, since we don't know, not only don't we know how many u's there are versus how many v's, but we also don't know the order in which they come, the order in which to interlace them, in general. In any specific case, if we've given the matrix A, and we know its eigenvalues, then we can figure that out. But like in general, we don't know. For like in the abstract situation, where we don't actually know the matrix A, we just have some symmetric matrix. Okay, so for that reason, it's good to permute the variables. We can just basically do a permutation of the axes. So this is also a rigid motion. Okay, it's not really a motion at all. It's just like a change in the coordinate system. If you think about it, suppose you have 3 space, and your axes are labeled x, y, and z. So if for convenience, you can just relabel the axes. It doesn't change the fundamental geometry of any particular set in 3 space that you want to study. Like what you call the axes doesn't affect the actual shape of the set. So if it's convenient, you can relabel the axes. What you called the x-axis, maybe you want to call the z-axis now. And what you called z originally, you can call y, or whatever. So we can just do a permutation of the axes. And that's the passive viewpoint. Now from the equivalent active perspective, what we're really doing is we're applying like a permutation matrix. Okay, a permutation matrix is just a matrix that takes the original coordinate vector, which in this case is these y1 tildes in that order, and then you multiply that vector by this permutation matrix, and you get some reordering of those vectors. The result of that, let me write it this way. If the permutation matrix is capital P, that's going to be some d by d matrix, and it's a matrix consisting of just zeros and ones. A permutation matrix always has just zeros and ones in it. Okay, but anyway, when you multiply the vector y tilde by that permutation matrix, what you get is some permutation of y tilde. It's like some specific permutation, let me call it sigma, basically acting on the vector y tilde, in the sense of permuting its components. Okay, so the resulting vector, what I'm calling p times y tilde, or you could call it this, the resulting vector has the same exact components, but in a different order. And so you can write it this way, for example. You can write it, I'll just quickly write this down and then delete it, because we don't really need it. But like sigma acting on y tilde will just be something like this. It'll be y tilde sigma of 1. Y tilde sigma of 2. Right? So sigma of 1 is just the first element of that permutation, which could be, let's say, 7. So you'll have like y tilde 7 as the first component. Then maybe sigma 2 is 3. So the next component will be y tilde 3, and so on. All right? So that's, from the active viewpoint, we can think of it as a transformation. There's a linear map based on the matrix P. There's some linear map based on the matrix P. And by applying that map, you're essentially just permuting the variables. But you're doing it via an active transformation, namely this linear map right here. Okay, so by including that step, we can further reduce the set. So I'm like, not only do I want to include this isometry, but I also want to include one more stage where we apply that permutation map. And the permutation map is going to be something that is computable, just like these two things here were computable. So let me modify this and say all 3 of the following objects are going to be computable. So I'm going to include there the permutation, sigma. And all 3 of these are sort of known to us, are computable. Okay, so that permutation is the permutation that the matrix capital P is based on. There's this correspondence between permutation matrices and permutations. Okay. By the way you get the permutation matrix, it's pretty easy. Let me just go to a new slide here. So I want a matrix that's going to send the vector x1, x2, x3, etc. to the vector x sigma of 1, x sigma of 2, like that. So the question is, what do I put here? Right, and you can see that we have to look at the first row and combine it with this column to produce this entry. And what we'll do that is just putting a 1 in the sigma 1 column, and then zeros everywhere else in that entire row. Because you see that when you combine these two by taking essentially their matrix product, you'll get like 0 times x1 plus 0 times x2, etc. And then you'll have a 1 times x sigma 1. And then a bunch more zeros. So that will indeed produce x sigma 1. Okay. So you see that P is constructed by doing the following thing. In the first row, you'll have the vector E sub sigma 1, but you have to transpose it into a row. Okay, so E sub sigma 1 is like the standard basis vector that has a 1 in the sigma 1 position. Right, then the next row will be E sub sigma 2, which has a 1 in the sigma 2 position, but transposed. And then you have like the last one. So you see that it just consists of a bunch of zeros and ones. And in fact, there's only a single 1 in every row. Each row has a single 1, and no two of those ones are in the same column. Right? So in fact, every column has also just a single 1 in it. Right? The reason for that is because sigma I and sigma j are distinct, if I and j are distinct. That's part of what it means to be a permutation. Permutation has no repetitions. So the column where the 1 is in the first row is the sigma 1 column, and the place where the 1 is in the second row is the sigma 2 column. But sigma 1 is not the same as sigma 2. So no two of those ones are in the same column either. So that's a good way to understand a permutation matrix, is that it just has a single 1 in each row. It also has a single 1 in each column. And then the rest of the entries are zeros. Anyway, that will multiplication by that matrix will implement that permutation map. And what we're going to do then is we're going to think of the set U here as the image under that permutation map of some set capital V. Okay. Now the equation here is wrong. I have to correct this equation. Remember that this equation really should read this plus M transpose Y tilde equals Q, and same here. Okay, and that's the set. That's the set I'm calling capital U. But again, we can make this simpler set capital V, such that a permutation acting on V will like restore the set U. Actually, it's going to be the inverse permutation, isn't it? P inverse, the inverse permutation. Okay, by an inverse permutation, what I mean is that like basically sigma is a map that takes the set 1 through D and maps it to itself in some order, and then there's an inverse map to that, sigma inverse. And that's also a permutation because it's still a one-to-one map from the numbers 1 through D to themselves. And you can implement that inverse permutation by the inverse matrix of the original permutation matrix. Okay, yeah, you can see that at every stage we had to invert, right? Like the rotation that we ended up using here is not R, it's actually R transpose, or in other words, R inverse. And then the translation vector that we end up using is not T, but rather minus T, so that we get the inverse translation. And then the permutation we're going to be using is actually sigma inverse, rather than the original sigma. Okay, for the same reasons. But anyway, the set V is going to have an equation that's essentially the same equation, but with the variables reordered. And so what the set V is going to look like is like this. We can put all the variables U first, and then all the V variables after that. So we're writing, basically this is just the old Y tilde. But we're writing that, okay, it's not exactly Y tilde, it's the permutation acting on Y tilde. By permuting the variables of Y tilde, the original Y tilde, which have the U's and V's interlaced in some unpredictable order, but we can permute them so that the U variables are pulled toward the front. All the U variables are pulled toward the front. And then all the V variables are pulled toward the back, toward the end. Okay, whereas the original Y tilde had some unpredictable interlacing. Like the original Y tilde could have been, U1, U2, V1, U3, V2, V3, U4, right? But now I'm pulling all the U's to the front, to the left-hand end, and then pulling all the V's to the right-hand end. Some permutation sigma does that, and we would just use that particular permutation. Okay, so then we can write the vector, which is still in D space, because we don't exactly know how many U's there are. We don't know how many V's there are, but we do know that there still have to be D variables in total. But you'll notice that we're now writing it as a concatenation of two lower dimensional vectors, U and V. And essentially what's going to happen is that only the U's appear in the quadratic terms. So there's going to be some quadratic form. Now, it's going to be based on a matrix, which is a diagonal matrix. I'm going to call it capital delta, with U plugged in. And then there's going to be some linear terms, which will have some constant vector. What should I call it? Yeah, maybe I'll just call it like H or something. So I'll have a row matrix, H transpose, multiplied by the vector V. And then we have like the whole thing set equal to the constant Q. All right, so you see that, what's this capital delta? That's a diagonal matrix. It just has on its diagonal only the non-zero lambdas. It's only the non-zero lambdas. So we don't exactly know how many of these there are. but it's a diagonal matrix, just like the original capital D, but here all of these are the non-zero lambdas, in the same order in which they originally appeared. All the non-zero lambda j's. Okay, so see that's a matrix of size r by r, r by r, and it's obviously diagonal, whereas the original D was of size d by d. So what I'm assuming here is that the vector r is not the vector r, the vector u is in r space. This value r is the number of u coordinates. So if the vector u is, let's say, in r space, where r is less than or equal to d. Okay. And then these constants involved in the vector h, so let's say the vector h is like h1, etc. How many of them will there be? Well, there are just d minus r of them, because the vector v has to live in d minus r space. Okay, but the important thing to notice is that the variables involved in the quadratic terms and the variables involved in the linear terms are now totally disjoint. Only the u's are involved in the quadratic terms, and only the v's are involved in the linear terms. So if we were to write out the equation in a kind of more longhand form, it would look something like this. You'd have u1 to ur, and then v1 to v d minus r. And then we'd have like lambda 1 okay, well, no, it's not lambda 1, it's lambda j1. The first non-zero lambda, right, times u1 squared. Lambda j2 times u2 squared, etc. Then lambda jr, ur squared. And then you'll have like h1 v1, h2 v2, h d minus r times v d minus r, all equal to q. So you see what the equation looks like. It's got a whole bunch of pure square terms. Let's say there's r of those with all non-zero coefficients. Every one of those coefficients is non-zero. And then you've got a bunch of linear terms in the v's, and the u's and v's have nothing in common. The u's and v's are completely disjoint sets of variables. Okay, so now we've got the original quadratic hypersurface S expressed in the following way. It's a rotation of a certain translation of a certain permutation acting on this set V. So we can understand S as the image of this particular set V, of this very simple type. Okay, and I'm going to call capital V the standard position of S. Okay, so this is like when you dealt with conic sections. If S was just some arbitrary conic section, like think of an ellipse that's tilted with respect to the axes and then moved off somewhere so that its center is not the origin. Take some ellipse, whose major and minor axes are tilted. They're not parallel to the axes of the plane, and then like moved off somewhere far away from the origin. That would be like the original S. But then by doing a particular rotation, a particular translation, and a particular permutation of the axes, we can always rewrite essentially the equation of the ellipse in standard position, where now the new ellipse is going to be centered at the origin and have its axes parallel to the coordinate axes. Okay, so that's like what V is relative to S. It's where we've written down some conic or quadratic hypersurface that has the same geometry as the original S. Same shape, but its position is different. It's been sort of brought to a standard position. Okay, so let's use that terminology. And all these mappings here are well understood and computable, and none of them change distances. Okay, notice that a permutation map also does not change distances, because by permuting the variables, the distance formula doesn't change. If you do it consistently to all points in space, change the ordering of the coordinates of all points in space in the same exact way, then the distance formula doesn't change, because the distance formula is just a sum of squares. And so the terms in that sum will permute, but the value of the sum will not. So distances will not change. So in fact, all three of these preserve distance, and therefore preserve the geometry or shape. So whatever shape V has, that's the same shape that S is going to have. So our task is to try to understand the shape of the set S. And by understanding the shape of V, we can do that. Okay, and so V has a particularly simple form. And it's that form that we're going to start using to classify all the different shapes that are possible. Okay, so let's just make sure we understand that in V here, all the quadratic coefficients are non-zero by construction. Every single quadratic coefficient is non-zero. However, the linear coefficients, h1, h2, up to hd minus r, these may or may not be zero. So you see that there are different possibilities. So for example, we can have a case where h1 is 0 and a case where h1 is not 0. Similarly with h2 and so on and so on. Right, and actually it really matters. whether a given linear coefficient is 0 or not. Okay, so let's start to ask ourselves, how it matters. What is the difference between one of these sets, capital V, in which, let's say, h1 is 0, versus when h1 is not 0? We'll try to understand that first, and then we'll come back to the quadratic terms. Okay? Now, the important thing about the quadratic terms will be the distribution of plus and minus signs among the lambdas. See, these are all non-zero, but what that could mean is that some of them are positive and some of them are negative. Or maybe they're all positive, or maybe they're all negative. And so the distribution of plus and minus signs, the distribution of signs among those numbers is going to have a big impact on what the graph looks like. Right? And then the nature of the h's, whether they're 0 or not, essentially, also has an impact that we need to understand. Okay, so let's start with the h's, the linear terms. We can pretty easily understand the impact of, let's say, one of them being 0. And the idea is simply this. If h1 is 0, then the variable v1 does not appear at all in the equation. All right, now when you have an equation it's supposed to be the graph of some object in space, right? But if one of the variables, one of the axes of space, corresponds to a variable that does not appear in the equation, then you see that that variable is completely unconstrained by that equation. You can assign it any arbitrary value. So if you assign all the other variables certain values that satisfy the equation, you can then take those values for those variables, and you can assign the missing variable any value you like. And what that means is that you can basically take some d-1 dimensional set, let's say, of solutions to the equation, and then drag that whole set in the direction of the missing axis. And all of those points, as you drag that object like parallel to one of the axes, you'll get what's called a cylindrical set. A cylindrical set in d space. Let me write this down. So the conclusion here is that the set capital V is therefore cylindrical with respect to that axis. With respect to the variable v1. Okay, so what it means is, okay, probably the best way for me to illustrate this is by a little picture. Let's work in 3 space. Imagine you have the equation, let's say x squared plus y squared equals 1, but thought of as an equation in 3 space, meaning I want the set of all points x, y, z that satisfy this in 3 space. So since z is missing from the equation, z is omitted, it's not mentioned in the equation, what you can do is just regard it as an equation in the xy plane. And as an equation in the xy plane, its solution set is the unit circle. But then you can drag that unit circle parallel to the z-axis, and every point that you reach in that way is on the resulting object. Like if I call the resulting graph G, any point that I can reach by starting from one of these green points and then dragging up or down in the z direction is going to be on that set G. So you see that you end up taking that entire circle and basically just dragging it up and down, and it gives you a cylinder, which is why these sets are called cylindrical sets. But it doesn't have to be a circle that you do that with. Right? For example, let's say I have the equation, so I want the set of all solutions x, y, z of the equation z equals y squared. So here x is missing. Now in the yz plane, that's the equation of a parabola like this. And then since the value of x is arbitrary, any point on that parabola can be dragged in the x direction, forward or backward. And all those points will still be on the resulting object in the resulting set. So what you get is a cylinder that has a parabolic cross-section. Something like that. We can call that a parabolic cylinder. Instead of a circular cross-section, it has a parabolic cross-section. But it still consists of basically the union of a bunch of parallel lines. Like this cylinder here was basically the union of all lines parallel to the z-axis that happen to pass through the circle, this cross-section. And in a similar way, this parabolic cylinder can be viewed as the union of all lines parallel to the x-axis that happen to pass through the original yellow parabola. Okay, so basically when an equation is missing a variable entirely, then the resulting graph is going to be cylindrical with respect to the axis of that missing variable. And by the way, you can have 2 missing variables. Let's look at an example like that. Let's say I want the graph in 3 space, so the set of all solution points of, let's say, just the equation z equals 0. Right? So if you just view that as an equation in 1 dimension, that is the z-axis, 0 is the only solution. But notice that I can drag that point freely in the x direction. And so all the points on the x-axis will be solutions. They all satisfy z equals 0 with an arbitrary x. But then I can also take any point on that yellow line and drag those in the y direction. Right, either way. So in other words, what is going to be swept out is in fact the entire xy plane. The set G here is just the entire xy plane. in R3. Right? And you can see that directly from the equation. You basically just have all points in space that have a 0 z coordinate. You can rewrite G this way, where x and y are just arbitrary reals. So the z is 0. Okay, and that's obviously just the points exactly on the xy plane. But you can view it as a doubly cylindrical set. It's cylindrical with respect to two axes. Okay, so in D space in general, like if D is a large number, then you can have a set that's maybe cylindrical with respect to a bunch of axes. So, for example, if D is 7, you can have some set that happens to be cylindrical with respect to 3 of the axes. And what that means is that in the remaining 4 directions, in the remaining 4 dimensions, you'll have some set, 4-dimensional set, that you can drag in a 5th dimension, creating cylindrical 5-dimensional set, then take that and drag it in some 6th direction, creating a 6-dimensional cylindrical set, which is now doubly cylindrical, and then take that and drag it in some 7th direction, creating a triply or trebly cylindrical set in 7 space. Okay? Just like in this process here, we had a 0-dimensional set, the red one, which we dragged in some direction, the x direction, creating a cylindrical 1-dimensional set. Then we dragged that cylindrical 1-dimensional set in a second independent direction, the y direction. Right? So that creates a set that's like doubly cylindrical in 3 space. Cylindrical, in other words, with respect to 2 of the axes. Okay, anyway, so can you have an equation that's triply cylindrical in 3 space? Well, you can. You can consider all solutions x, y, z of the equation 0 equals 0, right? And that's just all space. That's cylindrical with respect to all 3 axes. Okay, good. So if h1 happens to be 0, then the variable v1 will not appear. And because it does not appear, then the set is cylindrical with respect to that variable. So what do we do with that? Okay, well, what we do with that is we just try to understand the set resulting in dimension d minus 1 by just ignoring the v1 axis entirely. The problem then reduces in dimension by 1. We'll get a quadratic equation in d minus 1 variables. And if we can understand the shape of that in d minus 1 space, then we can just take that set and drag it in that v1 direction, creating a cylindrical set. Okay. Now, if a bunch of these h's are 0, then we're going to have, like, again, some lower dimensional quadratic. And if we can understand that, then we take that object and drag it in some direction, then take that resulting set, drag it in a second independent direction, and so on, until we reach back up to dimension d. Right? But with this reduction basically allows us to take any term where the corresponding h value happens to be 0, and just basically delete that entire dimension from the problem, reducing the dimension of the problem further. And the effect on the original set will just be to have some axes with respect to which the set is cylindrical. Okay? So that's the effect of the h's being 0 or non-zero. All right. Now, what if an h is non-zero? How can we understand the impact of that? So if you have any non-zero h's, then it turns out that we can make a further transformation to essentially combine all the linear terms into a single linear term. Okay, by making one more rotation of the axes, we can further standardize and get all the linear terms to be just down to one single variable. Okay, let me show you how that works.